Hello everyone, welcome to Structural Insights. My name is Shilpa Dixit. Today we will continue IS 2911 Part 1 Section 2 2010 for its Annexure B. In Annexure B, we will see the vertical load carrying capacity of the pile in a given soil profile. This code is for the design and construction of pile foundations. So let's continue. Here we are in Annexure B of the code, load carrying capacity of piles, static analysis. Now this B-1. This B-1 is for the piles in granular soils. Granular soils are also called sandy soils. And this B2 is for piles in cohesive soils. This is B1 and B2 are obtained with the help of SPTN values. If you have SPTN values or you have cohesion values, then you can use B1 and B2 and get your pile load carrying capacity, vertical load carrying capacity in a given soil profile. If you want to use the SPT cone test data, then you can use V3 and V4. But for the time being, we are skipping this part as this is not generally encountered. So we will basically stick to V1 and V2. Then we will move to Annexure C. Annexure C is for the laterally loaded files. This we will cover in next discussion. For the time being, we will restrict our discussion only to B1 and B2 of Annexure B of IS 211 Part 1 Section 2. So let's continue. So piles in granular soils. Suppose we have a soil profile. So let me just draw it. We have a soil profile. Now we have a file. This file is of circular cross section. This is D, diameter of the pile, and this soil layer has certain properties. So this layer has n is equal to 10. This soil is sand. Here this one is also sand, so n is equal to 12 sand. This is n is equal to say 5, but c is equal to 10 kg per centimeter square. Then we call it as a mixed sand and sandy clay. We may also have clay, complete cohesion. We may also have some n value in between. So this way we have a soil profile. Okay. Now we are applying some vertical load on this pile. When we are applying this vertical load on this pile, this load is taken by the pile and is transferred to the surrounding soils. So this pile will try to transfer this load through skin friction component like this and through end bearing in the given soil, right? So what will happen? The complete structural capacity of this pile will not be completely utilized if this pile is not resting on a very strong rock. That rock will behave like a footing for the column, and column may fail as a structural member. But this situation occurs only when the piles are socketed into the wood block stratum. But on the other side, when you have friction piles or piles in relatively stiff soils where you have good environment but there is no rock, then the pile load carrying capacity is not governed by its structural capacity. Pile may remain uncracked, but it may fail in vertical settlement. It may have a vertical settlement which is more than the permissible limits if one of the piles of a group, or under the building you may have say n number of piles, right? any of the pile, if it settles, then it will create a distress in whole structure. So we don't want our piles to settle by more than generally 12 mm. Then if that is more than that, then this pile is considered as failure. So we determine the axial load carrying capacity of the pile based on the surrounding soils. Okay, these values are important in this evaluation, N values and C values. Now, this if your soil is or soil layer, say this layer is a sandy soil, then you will use this formula. If this is a clay, see this one, only C values are there. So for this layer, we will use B2. Okay, B2 is here. Okay, for a given board log profile or for a given file, we may have to use B1 and B2 both together by taking the right decision based on the situation. So this file is ending here in this soil profile, right? So this soil can be sandy soil, which can have N value. It may have a C cohesive soil, which will have some C value, or it may be a C5 soil, right? So C5 soil will have N and C both. So based on that, we will have to find out in which soil this file is ending. Based on that, we will apply the end bearing resistance calculations based on V1 and V2 of the code. Now let's come to the V1. So if this soil, say this first layer, so I will just name the layer first, second, third, fourth, fifth, sixth, seventh, like this. Okay. So let's stick to for first layer, V1 will apply, right? For say fourth layer, V2 will apply, and for other layers, this will be V1. For all the C5 layers, V1 and V2 both will apply. Now we'll see what is doing V1. This is the main formula to use for V1. Similar type of Q is given in V2 also. Okay, so we'll see how they are defined. Let's continue. So Q is AP into half of D into gamma into N gamma plus B PD into NQ plus summation of I is equal to 1 to N Ki into PDI into 10 delta I into ASI. This is equation 1. Now this AP is the cross-sectional area of the pile. This pile has this cross-sectional area. So AP will be 5 by 4 into D square. Okay, I will write down it properly. AP is equal to 5 by 4 D square. Gamma is the density of the soil. First of all, you must understand that this first term before the summation sign, this first term, this is the end-bearing resistance, and this second term, this one, this is the skin friction resistance. So, end-bearing resistance, this calculation is to be done for the soil where your pile is ending. So, first term, you'll have to evaluate based on the gamma values of NC and Q values, not NC, in gamma and NQ. Q and N gamma values, phi values of this soil. And skin friction is valid for all the layers through which the pile has been casted. For all these values, you'll have to evaluate the skin friction component. This can be evaluated from the second term of this equation, this term. Okay. So for the end bearing component, what do we need? We need AP, this is the cross-sectional area of the pile, which is pi by 4 into D square. Then we have D, diameter of the pile, okay. Then we have gamma of this soil, where your pile is ending. N gamma value is the bearing capacity factor. This bearing capacity factor you will have to obtain from IS 6403. See here it is written. N gamma factor can be taken for general shear failure according to IS 6403. If you open your IS 6403, then there is a chart given where you will see that phi values versus N gamma values, or you can say there's a table here actually to give NC, NQ, N gamma, and different phi values. So these phi values are increasing and these values are also increasing. These values are for general shear failure. So let me just open this IS 6403 for you. Here we have this 03 1981. We are from then 2002. So in this we have this renal shear failure tragedy of bearing capacity factors. So here we can say this table, table 1 only. So we have NC, NCs, NQ and gamma for given phi value. So whichever say you have phi is equal to 30, then you will pick up your N gamma is this one, 22.40. So you get N gamma from here, then you go back to your code. So N gamma you have. Now PD. PD is the effective overburden pressure at the pile tip in kilonewton per meter square. Now we need to see the note 5. So what note 5 is saying is the effective overburden. What is that? Let me just explain briefly. So effective overburden is for a given soil profile. This is a pile. Now effective overburden pressure is gamma into H. Effective is gamma dash. Gamma dash is gamma dash is equal to gamma minus gamma W. Here gamma W is the input of water, which is 19 kilonewton per meter cube. Now we must understand that gamma H will increase as H is increasing. So ideally our gamma H should increase linearly from top to bottom, right? This is our gamma H. This value is gamma dash H. This should increase as your depth is increasing. But this for the piles case, this gamma dash H does not increase linearly from top to bottom. You will have to take actually up to 15 times T or 20 times T. Only up to 15D. D is a diameter. So 15 times diameter depth or 20 times diameter depth is allowed as per IS code. So what is that? This is 15D. This is 20D. So let me just come here. Here we must read this note number 5. In working out pile capacity by static formula, the maximum effective overburden at the pile tip means this pile tip, corresponds to the critical depth, which may be taken as 15 times the diameter of the pile shaft for phi less than or equal to 30 degrees and increasing to 20 times for phi degrees. So this what they are saying is if your phi value is less than or equal to 30 degrees, then your df effective depth is 15 times d. If phi is greater than or equal to 40 degrees, then your depth is 20 times d. So this phi 15 d is for phi less than 30 degrees and up to 20 it will go when phi is greater than or equal to 40 degrees. This is called effective depth. So here we have effective depth is equal to 15d or 20d. So it has to be taken care of. We cannot take gamma dash as up to full depth. This must be, this can create a lot of mistake if it is not understood properly. Now, we already know PD. Now we will see NQ. So in NQ what we have is, NQ we have a chart. Let's come down. This chart we will see for a given phi value. Say we have, for example, we have this phi value of 32. So 32 will come here. So for 32 we have this value on the graph. This will come here. So if this is 10, 20, 30. So this will be somewhere 40. So we will say N2 is equal to 40. So we will place N2 is equal to 14 here. Now we will see summation of I is equal to 1 to n ki. What is ki? For ki, we need to read this coefficient of work pressure applicable for the ith layer. See note number 3. So ki value is given as 1 to 1.5 based on your phi value 30 to 40 degrees. If your phi is 30, your I is ki is 1. If your phi is 40 degrees, ki is 1.5. This value will depend on layer to layer. Wherever your phi values are given for the sandy soils or the mixed soils where similar values are given, so you will interpolate your ki values based on your phi values between 1 to 1.5. Then PDI is same as PD. So you will have to be very careful, so that up to 15D or 16D of depth, up to 15D or 16D of depth, you will have to obtain your PDIS gamma into DF, whichever DF you have. Okay. As soon as you, based on your pi values, so your critical depth is 18D. Up to 18D, your PD will be gamma dash H. After 18D, you will have to keep your PD equal to 18 times D into gamma dash. It cannot increase beyond that value. So that should be taken care of. Now 10 delta I. So delta I, here we see this note, see delta I, angle of wall friction between pile and soil for the ith layer. So angle of wall friction is may be taken as equal to the friction angle of the soil around the pile stem. So wherever your phi is given, here phi is given, wherever n is given, phi must be given. So whatever phi is given, you can take phi is equal to delta for this calculation. Generally phi is delta is 2 times 2. Generally delta is defined as 2 by third of phi, but for this code delta is equal to phi in this equation. Now ASI is the surface area of the pile shaft in the ith layer. So for this fourth layer, your ASI will be this depth. Say this is a H4 with this height. This H4 into 5D surface area. Surface area for this step of the pile is ASI. So all the surface components for different layers of soils are to be obtained from this second term for all the sandy soils or C5 soils, and the end bearing component if your pile is ending in the sandy soil from this component, and if it is ending in the clayey soil, then from first component of B2, and if it is ending in C5 soil, then you will have to use both the components and see which one is best suitable. Now let's this completes this expression to you for B1. Now we'll come back to B2, piles in cohesive soils. So piles in cohesive soils will not have any component which will depend on N. Here QU is AP into NC into CP plus summation of I is equal to 1 to N alpha I, CI and ASI. AP is the cross section area of the pile. Is similar to this is the cross section area as I already discussed. NC is 9. Here we can see bearing capacity factor may be taken as 9. CP is the average cohesion of the pile tip. This will be given in the board log data. Here if this pile is ending in this layer, this bottom layer, 7th layer. So whatever value of C is given in this layer that we have to take here. So C is given. Units must be taken care of. It is in kilometer per meter square. Then summation alpha I. Alpha I is to be interpolated with the help of CU. Whatever CU is given of your in your board log data, from that you will have to pick up CU here, and then you can get your alpha here. Say your CU is given as 100, so you get this point in the graph, and from here you interpolate this, so you get somewhere around 0.4. So this is your alpha. So alpha will put for the given layer in a skin friction component here. Then CI of the given layer, C cohesion of the given layer, which is given in the board log data, and ASI is the surface area of the pile in that given soil layer. So this completes B2. So based on this B1 and B2, we can get the vertical pile load capacity in skin friction and end bearing, whether the soil is a sand or clay or it is a mixed soil, C5 soil. So we will evaluate one numerical where we will take up a bowl of data from a random soil in India. Then we will assume that the given n values or taken n values are corrected ones, and from those n values or C values, we will evaluate the axial load capacity of the pile, and we will solve that problem and we'll see. We'll discuss the conclusions. So thank you for being with us. We will discuss this Annexure C in the next video. Thank you so much.